Well, welcome to the Good Medicine Podcast. I'm excited today. Joining me today is John Lippert. John is the founder and I think you're the chief technical officer now. Is that correct?
Yes.
Of Scientia Vascular. Scientia is a cutting edge medical device company that specializes in innovative vascular access devices. And we're going to talk about what that means.
And therapeutics.
And therapeutics, yeah. and what minimal invasive procedures that John's been involved with to really revolutionize the way we deal with cardiovascular, cerebral vascular disease specifically. So, John, really great to have you here. John's one of my favorite people in the world. I really enjoy hanging out with John. I learn something new every time, so I'm excited to have this discussion with him today. I always ask people about their background and how they actually got interested in being involved in developing new medicines or new medical procedures. And I know a little bit about your background. I know you're a California guy that went to college to become an engineer. And so maybe you can tell us a little bit about how an engineer ends up developing new approaches and devices for treating medical conditions.
All right. We'll take a stab at that. But anyway, thank you for having me, and thank you for the accolades. But coming from you, that means a lot because you're one of my most admired people on the planet. And at my age, I'm older than everybody. So now I have a mentor who's older, who's younger than I am. So I appreciate your mentoring and helping me. So that's great. Yeah, medical devices. I wasn't always in medical devices. I went to graduate school in microfabrication, Chemi EE combined major, and I ended up making really small things, and those were semiconductors. So I went close to my hometown in Silicon Valley and started making semiconductors. I love technology, but there's really not a lot of identification with the product when you're in semiconductors. You look under this thing, and it's this small devices. You don't know if you're making a telecom device or microprocessor, and there's no connection to end user, certainly not to patients. And I'm pretty much of a people person. And so a friend said, we're making this new thing called cardiovascular stent, and we're going to use photo etching for it. That was a misnomer. They didn't know what photo etching was, but
they thought they were using.
Thought they were using photo etching, but I went and looked at it and became very interested in it, and started spending all my time in cath labs with doctors, asking questions, and it was amazing, and it got me all excited. The idea of using the great vessels of the body as free ways to end organs, to treat end organ disease, it was just amazing. And I loved the identification with the real end user, which is the patient, or like I like to say at our company, it's the patient's family that you should be thinking about.
That's right.
They're the ones that really have the purest motives, even more so than the patient.
Yeah.
But to be close to them and help them for an engineer is great. I grew up misspent youth working on cars and auto mechanics, and I was probably more cut out to be a mechanical engineer, but I was a chemical engineer. Yeah. And then I did the Chemi EE graduate work and ended up in semiconductors, and then totally flipped on its head and went into medical.
Yeah, it's always fascinating how our journeys are never straight lines, right? They wander around a little bit, but it's amazing when you find what you feel like, hey, this is what gets me up every morning, and this is what I can get excited about. And I can relate that I started out as a chemical engineer as well.
Yeah.
That didn't last very long for me. I think I took my first engineering class and thought, yeah, this is my thing. So I think we both ended up in the right place. Just took a lot of a different path to get there. But I find what you do very fascinating, and I love the idea that the major vessels of our body can be a conduit to deliver procedures and therapies in a very different way, and I don't think that's a relatively new notion. That we can access things from our blood vessels in both veins and arteries that we can stick things in them and move them around. And what I find interesting and just exciting about what you've been able to do. So you started with stents, which I think most people are familiar with stents. I think most people have had family members or people that they know that have had cardiovascular disease that have been treated with stents. And so I'm not sure how many people know how those stents actually get into the where they need to be, into the and mostly into the heart. We do stent other places as well in the body, but it's all essentially the same thing. And really where you ended up is on developing devices that access our vasculature, our blood vessels. And tell us a little bit about that journey and how you ended up with. So you started with stents, and then really kind of worked on the technology to how to get the stent to the right place, and how did that happen? And and then we can talk specifically about the technology that you discovered or developed to improve upon what people were using.
Yeah, that's a interesting story. I think it's interesting, but everybody's excited about the therapeutic. Oh, you got a stent? You got a stent?
Yeah.
And I went in, and in neuroanatomy, it's even more the case, which is getting there is the difficult thing.
It's more than half the battle, right?
More than half the battle.
Yeah.
And a lot of docs will say, yeah, I can get anywhere. But, it's like saying, well, I got into the show. Did you go see the show? I got into the show, but they locked me in the bathroom. So I didn't get to see it.
But I got there.
Yeah, I got there. So it's what you can do when you get there, which is really important. And when I started up my company, I left Target Therapeutics, which is a neuro company, and I talked with the guys, well, you're going to make something as mundane as a guide wire, and that's not important and all that. And it is sort of lowly, but it's the one tool that the doctors can't live without. They have to have it. And we made a huge improvement on my first company with that product.
So tell us what a guide wire is.
Oh, I'm sorry. Yeah, a guide wire is like a piano wire, if you will. It's ground down on the tip so that it gets real soft. Of course, it also makes a spear when you do that. So you put some kind of a platinum coil, like a spring on the end, so it's soft and doesn't poke through. So that's the rudimentary guide wire from the 60s is made that way. And a lot of them even today are. But a guide wire goes up. You have to be able to push it. You have to be able to torque it and turn it, put with a little curve on it, and get someplace. And it's kind of like they've likened it to pushing a rope up a hall and trying to drop the end of it into the bathroom and then maybe get into the medicine cabinet. Yeah. So it gets pretty difficult to do. So
how big, how big are these wires?
Well, the guide wires, they range, the workhorse guide wire in most fields is 14 thousandths of an inch. So
so compared to a human hair, what does that look like?
No, that's about 4 human hairs.
Yeah, isn't that incredible?
Like that. Yeah,
it's like you're taking 4 human hairs, and how long are these wires?
Yeah, so they're about 2 meters, 200 centimeters. The dimensions in our business are all kinds of things. They use millimeters, they use French size, they use thousandths of an inch, they use all kinds of different ones. So
funky measurements.
The wire is 14 thousandths, but it's 200 cm. So anyway, so you push it in place, and then you push a catheter over the top of it using it as a rail, and the catheter is real wimpy, soft plastic. It gets there, you pull the wire out, then you deliver the therapeutic in there.
So the way these minimally invasive surgeries work is you access an artery, and it's either in your leg.
It's a femoral artery, so it's right in the groin area.
In your groin.
You go up there, so you're puncturing a very, very large vessel.
So you go and puncture that vessel, stick that little skinny wire in there, and then move it all the way up into the blood vessels.
It's a little bit more complicated. You probably don't want to go into it, but the blood at that point is rushing very rapidly downhill, and you have to swim upstream.
Swim upstream the whole time.
So it's better if you can get the wire to a place that's going downstream.
There you go.
So what you have to do is you put in what's called a guiding catheter, which is a bigger, stiffer catheter that goes in the big vessels, the great vessels, including the aorta, and you go up and you drop it into the osteum of the vessel that you're interested in, if it's a coronary artery or if it's one of the major arteries of the brain. You go in at the top of the arch and you go in. So you have carotid, common carotid, et cetera, vertebral, and you drop it in. Now you're going downstream, and now you stick your product in there, and now it's going downstream and it's actually helping with it.
Yeah.
In fact, the early devices were flow directed. You threw them in there, and they would that would pay out this
Just
really
go with the
wimpy
flow.
stuff and go with the flow.
Yeah.
Because it turns out that for a lot of diseases, especially AVMs,
Yeah.
the higher the flow, that's where the problem is. So it'll just take you right
Take
to
you
where
right
the
to
disease
the problem is. Yeah.
Yeah. So that's interesting.
That's pretty amazing.
So that's how it goes. But access is the difficult thing.
Yep.
And when you get into stroke, we have a saying, access is therapy at our company, because you actually use the access device for the therapeutic procedure of doing a thrombectomy, aspirating that clot out of the brain. But the interesting story was this. I used to go into a cath lab and I would watch a procedure. Let's say we're doing a coiling procedure on an aneurysm. So I would ask the physician after I would track how many minutes were spent on each part of the procedure.
Mm-hmm.
And so maybe the procedure would last an hour and 15 minutes, 75 or 90 minutes. I'd ask the doc, I'd say, how much time do you think you spent accessing, and how much time, of course, the coiling, you're in the aneurysm, you're deploying this therapeutic device. It is the procedure. I'm doing a coiling today.
Yeah.
Well, they had it exactly opposite. They would say 15 minutes for access and then an hour to do all the coiling procedures. I said, it's exactly the opposite of that. It took you an hour to get there. So they hold their tongue just right, trying to twist the wire and everything else. So that's where we came up with changing how we make guide wires. And we use microfabrication for that. We use a special computer-driven machine that puts about 6,000 features in a 35 cm distal end of that. There are about 2,000ths or 3,000ths of an inch features, and we cut different sort of features and to give you the push, the torque or the torsional strength to turn it, as well as the trackability. And of course, it has to be soft. And then of course, it has to be shapeable, because the tip has to have a shape on it to make the right and left turns that you have to make. So anyway, that's what we do. So the doctors get engrossed in their procedures. They're very, very difficult, and they lose track of time and they lose track of what they're trying to do. They're just trying to get there. So I said, this would help the patients the most because they're being irradiated that whole time.
Yep.
And all sorts of other problems. As you know, the longer a procedure goes, surgery or whatever, the more chance of complications. So we like to speed things up, make it fast and easy to do. So that's what we did.
Yeah. So the good old days. So let's say, the types of surgeries that you have revolutionized, so I think most people are familiar with what goes on in the cardiovascular and the heart and cardiovascular disease with putting stents in, and the same kind of wires are used to guide those catheters and then deliver the stent. What you've focused a lot of your time on is what's going on in the brain, and obviously brain's pretty important. The heart is as well. Yeah. But for every minute that the brain is losing blood flow and oxygen, it's brain cells are dying, right?
2 million a minute. This is National Stroke Month.
Yeah,
so
that's right. Yeah.
2 million a minute. So you really have to get there. And there's no surgical backup. So the brain.
What's the alternative? You can't just crack open your skull.
In the coronaries, you can rapidly, if you have a dissection, you get a tamponade or something, you can just crack the chest and dive in. It's not the greatest, and it's not foolproof, but it can be a backup. But you don't have that option in the brain, and even if you had the time, a lot of parts of the brain are just not accessible. You have to kill so much parenchyma to get to what you need to actually work on.
You might be doing more harm than good.
You might be doing more harm than good. So, and then it's got the blood-brain barrier, so therapeutics can't get across there. Right, so we're working on that problem.
Yep.
So it's really the next frontier. And the brain is, it's regionally specific. Mm-hmm. So with regional specificity, any 2%, any 3 cc's of brain parenchyma might be a really, really critical function. And what's really interesting is where we're going with imaging technology and such is that the brain is going to be an incredibly big area that we're going to be working on, because we're just learning more and more and more. There used to be a saying, "Oh, that's just neuro." That's just neuro. That happens in neuro.
Yeah.
But right now we're able to determine real, very, very small parts of the brain that are affecting very important areas, and we're able to correlate those now. And AI is going to help us with that by quite a bit. and then we're able to treat it. And then so smaller devices that can to get to the very, very distal reaches of the brain are going to become more and more and more important. And then we'll do drug delivery, which is your business.
That's right.
And drug delivery is great. We can, we've done some of this work, but chemotherapeutics are nice because we can do a very, very high local dose.
That's right.
And a low systemic dose. So some of these drugs that have a really efficacious, however, they have side effects that we're worried about, and you can really reduce those
by limiting local delivery and
local
systemic
delivery. Yeah,
exposure.
So it's an exciting area, and we have other technologies we want to do. We want to use other parts of the brain and other parts of the vasculature to deliver and do cell-based therapies, cell-based delivery, which is even more difficult to do. But that's where it's headed.
Yeah, that's incredible.
Biohive is a nonprofit building the future of healthcare innovation right here in Utah. As one of the nation's fastest-growing life science industries, they bring together scientists, entrepreneurs, students, and companies to create breakthroughs that save lives and strengthen our economy. Whether you're in a lab or at a startup, Biohive is here to build, brand, and bring together a thriving life science community, and there's a place for you. Learn more, get involved, and see their latest happenings at biohive.com.
So I thought it'd be interesting for people to kind of hear the patient's journey of the typical stroke patient. So there are two types of strokes. There's hemorrhagic and ischemic. And ischemic is where you have a blood clot or you have an obstruction that stopped the blood flow in the brain. Hemorrhagic's kind of a little different. It's there's been a rupture of a blood vessel that's leaking out blood, and so both of them are problems. But you just mentioned that when a person, so the patient's journey, you throw a blood clot into your vasculature, the blood circulation in your brain, and it's cutting off blood to the brain. Every minute you're losing 2 million brain cells, and so some of us can't afford to lose. Some of us hopefully aren't losing any brain cells because I don't have many to give up anymore. But it's just an incredible, so the person has the stroke, their family member sees that they're having a problem, they call 911, the ambulance comes and gets them. So if they catch it early enough, they can give them some medication that potentially can help try to break up the clot. But most of the time, you have to go and get rid of that obstruction. So walk us through with your technology that you've developed, how fast that you can, get access, get that guide wire up there, get the catheter up there. I mean, we're going from your leg to your brain and these tiny little blood vessels in your brain. You have to find where it is using imaging to find where the obstruction is. Tell us how all that happens. How fast does it happen? And how is it different now than it was even 10, 15 years ago?
Oh, it's way different.
Yeah.
But before I start, something you said, you call 911, and so I'm going to say something that's a little bit controversial.
Okay, all right.
And that is that there have been studies done, and they show that if you call 911, that's an indicator for a poorer stroke outcome.
Interesting.
The reason is that it takes longer to get you to the hospital. And
so your recommendation, you see your loved one, you rush them to the hospital yourself.
And number two is that they don't know what they're doing.
What to do,
And they don't know, and they take them to a regional hospital or what happens, anyway. And this is a bit of a problem.
Yeah.
So you know.
But time really matters with these people.
Time matters. We did a little study on our brand new guide wire, which is 35 thousandths of an inch, which is, people say, you're going to put that in the brain? That thing is enormous. And it's actually bigger and softer.
Sounds pretty small to me still.
It really works great. And we're able to take, on average, about 30 minutes off of the total procedure time. So we can take it, if you use our real rapid system, you can clear a clot in sometimes under 5 minutes, under 4 minutes, and sometimes they take quite a bit of time, and they'll take what they call multiple passes to try to get there. So that's what happens. So when you have a stroke, you grandpa. That's what I am nowadays. I'm a grandpa.
Me too.
Grandpa's watching the football game, and all of a sudden you don't realize it, but he's not quite himself.
Yeah.
And then he realizes he might have a little bit of a hemiplegia or something, or aphasia. And, and what do you do? So they call 911. So the foregoing notwithstanding, they call 911. You take them to the hospital, and let's say you take them to a primary or a comprehensive stroke center. What you really want to do is take them to the comprehensive stroke center. And I just feel compelled to say that to everybody, no matter who I meet on the street, go to a comprehensive stroke center, because that's so important.
And how does somebody find a comprehensive stroke center?
Well, there's only 2 in Utah,
Okay.
and you should know where they are. And we'd like to work on a software package and give it away to people for free. It'd be a great thing for humanity to have your phone to tell you where you are right this instant, where the closest comprehensive stroke center is, and how to get there.
Yeah.
That could be sold, but we'd like to give it away.
Sure.
I got to find somebody that'll do that for me. But anyway, so you go to, and the first thing you do is you do a CTA and do a CT angio, and you look and you find out whether it's hemorrhagic or whether it's ischemic. When I was a kid, the only kind of stroke there was ischemic. They called everything else a brain hemorrhage.
A brain hemorrhage, yeah.
or an aneurysm. Hemorrhage. But now they've kind of, since the symptoms are somewhat similar, but 85% of strokes are ischemic in nature. So you go in, the first thing you have to find out is, the instant you find out that it's an ischemic stroke, it's a blood clot, a thromboembolic event, you've got something, then you start them on TPA. Now, that is not going to be a curative treatment, but at least it's a start. And you start that. And then if that center is also a comprehensive center, they'll wheel you right back and take you into the cath lab and do a procedure. They'll go in and they know where they're going, they know how to get there, and then they use one of our products, guide wire and a catheter that matches. And that's the thing. We're the only company that does that, which is match the guide wires and the catheters. Seems obvious, but most of them aren't. They pick out a wire from Carl's Jr.'s and a catheter from McDonald's, and they put them together and they say they must work, and it's not how it works. But anyway, so we have they drive up there and then they pull the clot and see what happens there with the patient. But here's another interesting point. And I'm not going to make any points with a lot of people out there with, first of all, don't call 911. Here's the next thing. I'm not going to give you any point, but I feel compelled to do it.
Okay, sure, yeah.
If it helps patients. I go to the very top conferences. I'm not bragging. They're not put on by me. I just go and sit in the back and listen.
Yeah.
And they're the very, very top cutting edge. So I have access to that information. And they did a little presentation, and they said, the process is the same. You go in, CTA, hemorrhagic, no. If it's ischemic, give them TPA. Just that. Those are identical steps in both hospitals, primary stroke center or in a comprehensive.
Yeah.
And we won't even talk about other hospitals.
What happens in a normal hospital? Yeah.
But it takes 45 minutes on average longer for the primary stroke center to give TPA than it does for the.
And what's the reason for that?
The mentality, in medicine, you never panic. Everybody's when you're a lay person like myself, who's grew up just whatever, and hospital's a black box, unknown, and you walk in, everybody seems to be calm. You go, this person's sick.
Yeah.
Relax. Here's how we're doing it.
Right.
We're doing it like that.
Yeah.
Everything else, you got to follow the old adage with stroke, which is don't panic, but if you are, make sure you're the first, and when it's you want them to panic.
Oh, absolutely.
And guess what? If you saw what happens in a cath lab when they're doing a stroke, and you're familiar with how hospitals operate, you step back a little bit, and you actually physically do. You stick back in the control room, and you just watch, because it is a different scene. People are working so fast and furiously. They're pulling things. They're tearing open sterile packages. They're throwing it onto the sterile field. Somebody's working, prepping something else. I mean, it is a crazy, crazy world. And if you go to a comprehensive stroke center and you walk in the emergency room and they say, I think I'm having a stroke. Everything stops.
Yeah.
They grab that person. No matter what happens, someone's bleeding out, just leave them. Go on, grab this person. That's not the same. I shouldn't have said
a little
that.
facetious, but
It's crazy.
But minutes matter.
Minutes matter, and they jump on it and they get it done. And
Yeah.
we're looking at all kinds of ways of doing it. So you can actually do a spiral in the cath lab with a biplane. So you put the patient in, and you're under continuous X-ray fluoro with 2 C-arms that are doing X-rays, where you can put those things in CTA mode, and you can actually do a CTA with those. Of course, the radiation dose is a little higher, and
so just so everybody knows, the CTA is a CT angiogram. So it's using everyone knows what a CAT scan or a CT scan, but an angiogram is actually looking at what's going on in the blood vessels.
In the blood vessels. So you want to see that. So what somebody brought forward at another conference was 10 years ago, it wasn't so long ago, and it wasn't ancient caveman medicine.
Mm-hmm.
We were doing real things.
Yeah.
Here's a picture of a full-blown permanent CT gold standard up from then, and here's what a CTA looks like when you put them on this kind of low quality in the angio suite, and lo and behold, it's better today than it was for the whole full-blown permanent facility for CTA. So the point was, if this person comes in and think they're having a stroke, don't take them to a CTA, take them to the cath lab.
Yeah, and
do a
it
spiral right on the spot.
Yeah.
And immediately go in. If it's hemorrhagic, then you've got to you've got to change the sheets.
That's different,
and that's a loss. But everything else is a lot faster. So
well, it's
interesting.
It's interesting. Just going through that journey, it tells you something about we're the Good Medicine podcast, and one of the things about surgical procedures, especially, is that if you have a choice, which sometimes you don't, but if you do have a choice, it's always best to go to a place that this is what they do all day long, every day.
Right.
It's there's a lot of great surgeons out there that are they do a lot of different types of procedures, and we need those people, and they're important. But if it's me and you, like you said, if you have an option, if you're close, if you can get there, going to a place that this is what they do, and this is they have that procedure down. You just said that the difference between a primary and a comprehensive, which primary stroke centers they're built to do it to stroke patients. Comprehensive is that's what they do all day. They have dedicated people. That's what they do all day long, every day. 45 minutes. And we just said minutes matter, right? I mean, that's incredible. But I think it's an interesting thing that most people don't understand about medicine, is that it does make a difference when you're having, especially a life-threatening type of condition like this. The outcomes are different. They're demonstrably different between centers that are built and have a process and a procedure to move people quickly, that have the urgency to say minutes do matter, and instead of sending you down to the imaging suite where we're going to do this, let's just get you in the catheter lab and just do the imaging in there in line. I mean, it saves time and it saves lives. It saves brain cells, right? And that's at the end of the day, grandma and grandpa, you want them walking out of the hospital as functional as possible, right? That's what it's all about.
Yeah, and the other piece of that is just repetition. A lot of the basketball player shoots baskets day and night.
Yep.
You could take a great athlete, let's say a Tom Brady. He probably played basketball in college and high school. He probably knows how to handle a basketball. Who do you want at the free throw line when it's time? Tom Brady, who's a fabulous athlete, or somebody else who plays basketball.
That's all they do.
That's all they do.
And
you just get better. And that's where the outlying labs become an issue. Some people think poorly of those folks out there. I think more highly of them.
Sure.
For a person to go to a remote location, we got it out west here. We've got a lot of that, North and South Dakota and Montana and Wyoming and other parts of Utah.
Yeah, they can't really have a comprehensive stroke set.
How do you get? So robotics is going to maybe help us with that, and we'll talk about that some other time, I suppose. But the other thing is that in in these hospitals that do have a center because they have a large catchment area, it's still, they will not do as many procedures.
Yeah.
And but thank God that they're there. They're willing to work in these remote locations. They're not going to get a lot of notoriety. They're not going to get a lot of money.
Yeah.
But they're out there living in northern Minnesota where it's frozen and
taking care of people.
Taking care of people.
Yeah.
And we're grateful to them. That's again one of our passions at Scientia. We want to make an equalizer.
Exactly.
We want to make a device that makes you as good as that doctor.
That's where I was going.
So much technique involved. That's the problem with our procedure.
Yeah.
Is normal vasculature in the brain occurs about 33% of the time. So
so normal's abnormal.
Yeah, the circle of Willis. Everybody's familiar with the circle of Willis. You see the drawings of the circle of Willis.
Well, we're familiar.
Yeah.
I'm not sure everybody is, but yeah.
Okay. Well, the circle of Willis is something that you learn about, but the normal circle of Willis that's taken as the standard, that occurs. What percent of the time do you think that occurs?
20%.
11%.
11%. Okay.
11%. So the circle of Willis is 11% of the time the way you think about it. Everything else are variants on that. So you look at it and say, how am I going to get into this thing? I've got a PCA, posterior communicating artery, part of the circle of Willis. I have an aneurysm there, or I want to access through there. How do I know where the takeoff is? How do I know what size it's going to be? How do I know how to traverse this thing? And it's very, very difficult to do. And so you find out when you get there.
Yeah,
and then when you get there, you've got to have a tool that has the robustness, the design capability, that has the flexibility that can do all these procedures. Yeah. That's what we're trying to do.
And that's amazing about, and that's what's exciting to me about technology in medicine is it is an equalizer, right? Because in the good old days of medicine, you were really, you literally lived and died by the skill and the experience of the person that was doing the procedure. And if they were skilled and experienced, then you had a better chance of somebody that wasn't skilled and experienced. But today we have a way to try to equalize things. And that's what's exciting, I think, about what you guys are working on is how do you make technology that can take a less experienced operator, or less, practitioner, and turn them into the outcome as good as somebody that does it all day long every day. And I think that's what's exciting about what you guys have done is that you have taken, like you said, I think at the beginning that people look at these wires and just say that's just a wire, right? It's just a piece of metal that that you stick, a little tiny little skinny piece of metal. But when you look under the microscope at your wire, there's a little bit different stuff going on there in terms of how it's been engineered, and that's fascinating to me. How'd you come up with that? This micro machining. So basically, so everybody knows what we're talking about. So he took this metal wire, this normal, solid wire that you, like you said, has a little spring on it to give it a little bit different characteristics. But you figured out that, hey, if I could go in there and make some cuts on that wire and change the physical properties of that wire in a way that it could be guided up through these crazy anatomies that, like you said, everybody's a little different. We try to, in the textbook, they show you this is what it looks like, but in reality, every patient's slightly different. I took gross anatomy, and the cadaver I was dissecting had some very strange anatomy. You're just like, what in the world? There's two ureters on one side. Just weird stuff like that happens. And that's the textbook drawing looks great, but then you get into actual people, and it's like, oh my goodness, this is not what I learned in the textbook. So what you're trying to do, and I think what you've done, and what's remarkable is allowed people to have technology that gives them an advantage that usually would take years of experience. And, I think you told me a few months ago that you had a case where a resident, somebody still in training, did a procedure and did it so fast that it was, that you would have thought that person had years and years of experience, and because of the technology that was in your device.
Yeah. In fact, the attending, our doctor, he called me on the phone from the control room and said, we can't get into this. And I told him what I thought he should use and how he should use it. And he called in and told him that. And he was scrubbing in to go in and help him. And he said, done.
By the time he got in there. And that was somebody in training, right?
In training,
yeah. That's pretty amazing.
So if you have the right tool, it makes it a lot easier. Yeah. So that's the issue.
Yeah, that's incredible.
Yeah.
So I guess I mean, it's I know you don't like tooting your own horn, but I mean, you've revolutionized how these procedures with the technology that you've developed. There's tens of thousands of people that have had procedures done with products that you've made, and I think without any kind of hyperbole, millions of people. Yeah, millions of people.
The first product I did, we were over 2 million.
Yeah,
and
incredible.
We'll do over 5 million. And it sounds like I'm bragging and tooting my own horn. But I'll just say this. I frankly don't know. People say that I'm creative. They say that I'm really smart and I really can do all these things. And I can't tell them, well, it's nothing, because then they say, well, I couldn't do that. And I can't tell them that I worked real hard. I sat down with my good friend Mark Eaton just a couple of weeks before he died, and we were chatting about it because he's helped me a lot in my life, and we went back and forth. We're pretty good friends. But I said, Mark, you never looked at me and said, John, why are you only 5'11"? Why don't you be at least 6'5"? I mean, it should,
Mark Eden was what, 7'4"?
7'4".
He's a big giant guy. Yeah.
And I don't know what I have, or I'll take credit for this.
Yeah.
That I worked like crazy and I begged people for money. You know that.
Yeah. Yeah.
and
the worst part of our business.
Worst part of our business. And I worked really hard, and I worked long hours, and I'll take credit for some of that. But why this stuff comes to me the way it does, whether it's a lot or a little, good or whatever, I don't know how it comes to me. But I have a different way of looking at things. First of all, I love technology, so we use finite element to map, which we've never done at any other company that I was ever at, and I don't think anybody else does. We know exactly what the radius of curvature is at any vessel at any point, any time in the brain, and we look at that, and then we determine what kind of flex you need, and we know how to do that. Flex goes as the diameter of the fourth power, so we have to duplicate.
Of course,
we have to duplicate that equivalent diameter with a micro machined, and we design those things. So we have all those tools to us. And then what I do, it sounds maybe weird or whatever, but I don't think of a macro thing and try to shrink it down and make something out of it. We have a lot of braided catheters. Well, that's the same as a garden hose. I got the idea out of a garden hose.
Braiding garden hose. Yeah.
I don't do that.
Yeah.
I like to sit. And I close my eyes and think of it. I think of sitting inside an artery and looking at it. And I'm in this thing. So like this room, for example, this is 3 millimeters. And, those little ceiling tiles, are 4/1000ths of an inch. And what am I going to do in this vessel? What does it need? What is the anatomy telling me I need at this spot? And I'll go in and I just try to
create your own virtual reality. You don't need those goggles.
Oh, that's right.
You just do it yourself.
I'm not smart enough to use the goggles. I don't know what they do. But
that's incredible.
Yeah, but that's what I do.
You just think if you're inside that vessel, what do I have to?
What's it doing?
What's it doing? Yeah.
What's that kerf on that one?
That's amazing.
0.002 of an inch cut. What's that doing to the vessel when it interacts with it? I've got endothelium here. What is it gonna do when I go past it? What do I need? What does the body need at that point? So that's sort of what I do. And then whatever else creativity comes about, it didn't come from me. I was just born with it.
There you go.
This is it. I'm 5'11", and I look at things this way. Those are two things I can't change.
That's just what I am. That's right.
So I don't know how it works, but anyway.
Well, what if you could get rewarded just for being healthier? Meet Galvin, the company using the latest blockchain technology to reward you for taking care of yourself. They help with your mind, body, and soul like a personalized health assistant to track your progress and help you feel better. Galvin's G Plus app rewards you for exercise and assesses your mental health in under a minute using AI and over 2,500 voice biomarkers. If you're feeling off, G Plus gives you personalized power-ups, science-backed techniques to help you feel better fast. And here's the best part. When you prioritize your wellness, you earn crypto. Ready to level up your health? Use promo code GOODMED20 at checkout for 20% off. Download G Plus today at the Apple app or Google Play Store and start your wellness journey with Galvin.
It's, obviously just looking back at all the things that you've done, millions of people being affected by products that you developed. So what gets you up in the morning now? Me. But you're not a spring chicken anymore. Are you going to keep doing this?
Please. Yeah, I'm 69. Yeah, so it's I'm getting.
But you're still passionate about this.
I'm on the shank end of life.
Love this stuff, and that's exciting to me to meet somebody like you.
Well, I'll tell you this. I'll tell you the story.
Yeah.
When I left semiconductors, my parents said, "What are you doing?" And they weren't college educated or anything, so they weren't familiar with a lot of things. But I told them, I said, "I'm going to use the great vessels of the body as freeways to get to organs and treat diseases there that the doctors come up with." And they could understand that. And so recently I had a conversation, I say recently, over the last 10, 12 years, I said to myself, in little moments of reflection, saying, well, a lot of life has gone by and we've worked on a lot of things and they've been successful. We've helped a lot of patients, but how many end organ diseases have I been treating? Well, is stroke an end organ disease? Well, basically in the brain, we're still working on the freeways.
Yeah.
I never
got off the freeway.
Yeah, the freeway's washed out. Okay, I got an aneurysm, or I've got a dissection. Right. Yeah. I'm going to treat that, or we have a mudslide, and it's the road is blocked, so I got to clean it up. I want to treat Parkinson's. I want to treat Alzheimer's. I want to treat these diseases.
Yeah.
I want to treat cancers of the brain. Now we're able to do a little of that in the liver. So HCC, we work on that, and we're able to improve some of the treatments with HCC, a chemoembolization or a radioembolization, and we're able to get closer to the disease and do that. So we're able to do that in the brain. We're doing chronic subdurals, hematomas. So those is a brain disease, and we're able to do it. But it is sort of the same thing. We're going to embolize and get rid of that bleed. But the real diseases of the brain, what can we do for those? How can we take some of the drugs that you're working on, and how can we get them there in a better way? I mean, the brain is now regionally specific again, like we're saying. So some of the therapies, not only do we only want to be in the brain, but we want to be only in one part of the brain.
That's right, exactly.
and the more accurate we can get there, the more bandwidth we can give to the pharmaceutical developers and say, you don't have to worry about this because you're not going to get any non-target therapy going.
Yeah.
It will be right at the location that you want to go to, so we can do that. So that's what gets me up, doing some of that. And of course, every good son, like you, every good son wants to avenge his mother's death.
Absolutely.
And so my mom died of a hemorrhage. And we presently don't have any treatments for hemorrhagic stroke. You pull a flap after 10 hours and try to reduce the swelling, and you got some midline shift, and you try to get rid of it and do this and that. Well, that's not treating anything.
Yeah.
They come in, we do a CTA. Oh, this is hemorrhagic. Well, what are you going to do with them? Well, give them some oxygen, and
we'll just see what happens.
Call their family.
Yeah.
I don't want that.
Yeah, that doesn't sound good.
That wasn't pleasing for me.
Yeah, I can imagine.
I want to go in and do something about that.
Yeah.
And so I've got some ideas on what we might be able to do that there intravascularly. So because you've got a hemorrhage that's deep in the brain, what does a flap do?
Yeah.
A flap releases the pressure after that hemisphere has already been crushed. So I don't want that.
Yeah.
So we've got to go in and treat it right on site and there. So anyway, so those are the things I'd like to work on.
Yeah, no, I think it's exciting to think about the convergence of what we do because I'm developing drugs that mostly we're just taking systemically, taking a pill, and it's going everywhere.
Yeah.
And we have to deal with we're trying to balance to say, okay, that little pill, it's just fascinating to me. It's a miracle any of this stuff works, right?
Yeah.
When you think about it, it's like has to get through your stomach.
How does it know?
Yeah, how does it know where to go, right? It's like, I got a headache. How does it know to go to my head, right? I mean, figure that out. So, so that's fascinating. And I think it's just intuitive. It's like, hey, if the problem's, I have a hemorrhage in my brain, I want to put something in my brain to fix that, right? I don't want to take a pill that's going to be delivering this medicine everywhere, because I don't need it everywhere. I need it there. And one of the things that I think we're starting to realize is that a lot of the consequence of these things that happen, these injuries, and whether it's an ischemic stroke or a hemorrhagic stroke, or some of the other things that happen in our central nervous system, it's actually the damage is caused by the response to this, and it's not necessarily, because we think about it, it's like, okay, you've got this clot that's blocking oxygen, but our cells in our body are pretty amazing at how they adjust to things. It's just like, well, crap, we don't have enough oxygen. Let's figure out how to get around that. But then all of a sudden you come in with your and you open that blood vessel back up, and then there's a big flow of blood back in there. We're starting to realize that actually causes problems too.
That's not good.
Yeah. So how do we fix all of that? And so I think there is a combination of procedural and therapeutic medicines that can be put together in a way that opens up new possibilities. And that's what I think, that's why we like talking, because we think, hey, what you do and what I do, I think there's some things that could happen there. And as you know, I'm very interested and excited about inflammation specifically. And I think that inflammation as a response to damage and injury, it's the normal process, right? I mean, it's what the body, when you have we call them damage associated molecular patterns or molecular signals. So the body recognizes this isn't right, something's wrong here, and part of the response is activating our immune system to say, let's go figure out what's wrong here and how to fix it. And that's one of the things that we don't do well with the surgical procedures is we can go and remove the insult or the obstruction or whatever it is, but the body still has to figure out how to deal with the consequences of that. And maybe there's some ways we could support that. So I think that's what we're thinking about, and that's what keeps you and I going, is the next thing, right? We made this much progress. How do we go to the next level?
Yeah, and it just doesn't happen fast enough.
It doesn't.
We've been thinking about it.
We talk about it.
So
we think
imagine
about it.
it's going to happen.
Let's quit thinking about it. Let's start doing it. And I think the hardest thing, and John and I are both entrepreneurs, so we've started companies, multiple companies, and I mean, the hardest thing for us is everything we do is so expensive. It is so frustrating, because we can't it's not like a software programmer that has an idea they're going to go down their mom's basement and start working on the computer, and basically there's not a whole lot of overhead associated with that. Everything we do is just so darn expensive. And so how do we get enough enough resources to really support what we do? And hopefully with success, hopefully that leads to more opportunities, and it does. But like you said, I think the most frustrating thing for people like us is the time. It's just we're not getting any younger, and part of the hard thing about our business as well is there's no replacement for time, for experience, right? I mean, we're trying to make tools that help doctors overcome experience, but the invention and inventive part of what we do, there's so much that is, you've been at this for a long time, for decades of work, of working on, so have I. And I can't pass that knowledge on to somebody else. It's really hard. I can't take a 25-year-old newly minted engineer or scientist and say, I'm going to give you everything I have. And that's where artificial intelligence really gets me excited, is maybe that's a way that we can actually enable the next generation, where they don't have to take so much time and so many gray hairs that we have. Those are a badge of honor for us, because we earned them all, right? I mean, that's a lot of stress and a lot of hard work. But I'm excited about the future of using artificial intelligence to hopefully once again augment what we can do and make people that don't necessarily have the years of experience, but have access to the knowledge and the know-how in a different way, right? And that's just, I mean, we're old enough guys that we look at that and say, what is this AI stuff? But I'm using it every day now, and it's just remarkable the possibilities of what can be done. And people ask me, "Aren't you worried that AI is going to replace you?" It's like, no, I'm
hoping that'll happen.
Yeah, exactly. I'm hoping it happens for sure. But I tell people we're the reason AI is invented, right? I think that the opportunity to adapt this technology to accelerate what we can do, hopefully make it faster and cheaper, and some of these ideas that you and I have been cooking for years now, talking about, let's do this, that hopefully that enables some of this stuff to become a reality, because I'm not sure we have enough time to do it the old-fashioned way, and we need to do something a little different and do it faster. So anyway, it's exciting times. I tell people, with all the stuff that is going on in the world right now, and all the uncertainty and chaos, and especially all the changes that are happening with our regulations and the government stuff that's happening right now, there's a lot of uncertainty. And I don't, the FDA that you and I are used to working with, I don't know whether next year it's going to look the same and whether it's going to be the same. But with all of that, I still am extremely hopeful for the future. I just think that we are just entering the golden age of medicine. I think that the discoveries and the progress that are going to happen in the next 10 years are going to dwarf what happened in the last 100 years. I really do. I think
it is very much exponential.
Yeah.
Knowledge is exponential. It e to the x derivative is e to the x. So it grows as fast. It goes faster and accelerates based on what's there.
Yeah, that's exactly right.
And it will.
I can understand that, but the math, that's why I'm not an engineer.
Yeah. Well, anyway,
biologists don't do any math.
Well, but it's a situation that they had the same worry, with computers are going to come in, and now we're not going to have anybody. Yeah. I mean, nobody's at plugging in your phone lines, and say, I want to call David Beers. Well, just plug him in, and it automatically happens. That person's out of a job, but there's other jobs.
Exactly.
So it's going to be,
like you said, we want to be out of a job.
Yeah,
or what
it's
going to
be interesting to see what is replaced.
Yeah.
What part of what each of us do is replaced.
Yeah.
And then what does that bandwidth allow us to do?
Yeah.
Otherwise, that's not being picked up. What is it? Which part is? And that's going to be very, very, very interesting to see how that works. And I think it's going to be good for humanity. There was a guy that wrote a book. I should know it if I'm on a podcast, but I don't. There's been about 4 books called Abundance, and there was one written, I don't know, about 10, 12 years ago. I think right around 2010, so 15 years ago. Abundance, and they talked about AI and exactly what he said is playing out. He said by 2025, we will have the hardware to outrun human thought, and it'll take till 2035 to get all the software in place to do that. And we're seeing that play out right now. And he said, there's going to be higher yields on crops, and it's going to take care of food, and overpopulation is going to go away because the more educated you are, the less kids you have, and we're educating everybody now.
We're seeing that happening.
All this other stuff. He said you got to quit worrying about the future and start being excited about what can happen.
Yeah.
And I thought that was probably pretty accurate. And for us, it'll certain things that we do, it won't. I wrote up a couple of documents and I handed them to. He took it to chat
GTP.
Yeah, and he gave them back to me. He said, I did some edits on this, and I didn't know he had passed. And I said, man, I didn't know what a great writer you are.
You're incredible. Yeah.
And I pride myself on being able to write nice missives and nice notes to folks. Yeah. That part of me is going to go by the wayside because everybody's going to be able to do that. Yeah. So I'll have to find something else that I can do. Maybe it'll be nothing, but I think
you go back working on cars.
Yeah, I'll be working on cars. Spend time working on other things, but but we'll see how it goes. And it's I'm optimistic, and AI is, it's when my first job I had when I got out of school in semiconductors, I had an office in a training building. It just so happened that he put the R&D group there. And I walked in. They were doing an artificial intelligence class. And someone said, artificial intelligence, this direction. And somebody had scribbled a note and said, real intelligence
That
this way.
Yeah.
But anyway, that's how long it's been around. We've been talking about it. And, is a spreadsheet artificial intelligence? It is. If you have a not and gate or something, is that artificial intelligence? It is.
Yeah.
And it's, so it's, in a certain sense, it's abject stupidity run at light speed. But it does all these great correlations for us, things that, spaces that we'll never be able to interrogate ourselves.
Yeah.
And it provides that information to us. So, and there's just no way that we're ever going to be able to look at that space, and they'll be able to do that. What's left over for our brains to do? Well, we don't quite know all that yet, but we'll figure it out.
Yeah.
It'll happen.
I'm excited to see that. Yeah.
It'll be good.
Yeah.
But in the meantime, we're going to have, we're going to be able to map out the arteries of the brain, and we're going to be able to tell the doctor exactly which products to pick, because there's a difference. You can select this diameter, that diameter, this length, this one, this flex, that flex, blah, blah, blah. All those subtle extras, they'll be able to select all of those for that patient coming in a helicopter. We'll already have the CTA. We'll have artificial intelligence doing the analysis of it and say, use the fastest way is this route.
This and this.
Use this. It doesn't look like it, but it'll be this. And that's all going to happen.
Yeah, it's all
and
happening.
It's going to be the same for outlying labs where a doctor does one a year, or the doctor does 1,000 a year.
Yep.
And it's going to be the same treatment. It's going to be really, really nice. And then the stuff we talked about in drugs and regional specificity and all that's going to, for the brain, is all going to be fabulous stuff. That's all coming. Yeah. And we'll be in place to do it. It'll be fun.
That's exciting. Well, I think that's probably a great place to end. So thank you so much for coming on the podcast. And it's I'm excited to see what the next thing is. And hopefully we got something that we're going to do together. We're excited about it.
We're committed to doing that.
Yeah, we'll get it done.
Thanks so much for having me.
Thanks a lot. Appreciate it.
Okay.
That's it for today's episode of Good Medicine. Thanks for joining us as we explore the science and stories behind health, medicine, and innovation. If you enjoyed this conversation, please subscribe to our YouTube channel. That's a great zero-cost way to support us. In addition, please click, follow, and leave a review for the podcast on Apple and Spotify. If you have questions or comments for me, please put them in the comments section on YouTube or reach out on all social media platforms at Good Medicine. Links are in the description. The best way to support the podcast is to check out the sponsors of the show. You can do this by looking at the links in the show notes. That's it for today. I'm Dr. David Beers, and we'll see you next time.